We know that vertical asymptotes are going to occur at places where our function is undefined. So to find them, the first thing to do is to identify any values of x where our function is undefined. So we want to keep in mind, though, that these values are just candidates for asymptotes. Just because the function's undefined doesn't mean we're guaranteed to have an asymptote there. They may just be open circles in the graph. So always remember we've got two different scenarios that can occur whenever we have an undefined function value. It's possible that we'll have a vertical asymptote, or we may just have a hole or break in our function. So finding the undefined values means we have one of these two things occurring. So then what we need to do is evaluate the limit of the function at those points, being sure to factor and reduce if possible. If we get some number as a result, so any real number, whether it's a fraction, whole number, negative number, then we have an open circle in the graph. If we take the limit or try to take the limit of the function as we approach that value, and we get a limit that does not exist, then we have a vertical asymptote. So let's take a look at a few examples here. In example 8, we're given the function 6x over x plus 4. So to find places where our function is undefined, we'll take the denominator, set it equal to 0. In this case, we get x equals negative 4. So if we take the limit as x approaches negative 4 of 6x over x plus 4, and then try to use direct substitution, we'll get 6 times negative 4 over negative 4 plus 4, which is going to give us negative 24 over 0, which means that the limit does not exist. There's nothing in the 6x, x plus 4 that we could factor or reduce, so since we can't evaluate that limit, we know that we have a vertical asymptote at x equals negative 4. In example 9, we want to proceed exactly the same way. Take our denominator, set it equal to 0, but before we can really do that and solve for x, we first need to look at factoring that expression. So this would factor as x plus 3 times x minus 4. Setting that equal to 0 gives us x equals negative 3 or positive 4. So this means we want to take the limit of our function as x approaches both 4 and negative 3. So we'll start with as x approaches 4. To look at canceling and reducing anything, we also want to factor the numerator here, which in this case would factor as 4x minus 1 times x minus 4 all over x plus 3 times x minus 4. So once we have everything factored, we can see some cancellations. In this case, x minus 4 over x minus 4, which means we're taking the limit as x approaches 4 of 4x minus 1 over x plus 3. From there, we can use direct substitution, and we would get a limit of 15/7. So since that limit exists as a real number, that gives us no vertical asymptote. So again, even though the function's undefined there, what we would have is just a hole in the graph or just a break. So if we take the limit as x approaches negative 3 of this reduced function, 4x minus 1 over x plus 3, if we try direct substitution, this will give us negative 13 over 0, which is undefined. So again, we get a limit that does not exist, which means we have a vertical asymptote at x equals negative 3. So it's possible we'll have a vertical asymptote for every value of x where the function's defined, or in this case with example 9, only at one of those points where the function was undefined. So similarly, we can look at an example 10, first factoring the denominator as x minus 4 times x minus 6. I'm sorry, that should be x plus 4 times x minus 6. Setting that equal to 0 gives us x values of 6 and negative 4 to consider. If we take the limit as x approaches negative 4, first we'll factor the numerator as well. So that'll be 3x minus 1 times x minus 6 all over x plus 4 times x minus 6. So again, once the numerator and denominator are factored, we can see some cancellations, which gives us the limit as x approaches negative 4 of 3x minus 1 over x plus 4. So if we try direct substitution, we'll get something divided by 0, which again tells us that this limit does not exist, which means we have a vertical asymptote at x equals negative 4. If we try to take the limit as x approaches 6 of this reduced function, 3x minus 1 over x plus 4, direct substitution in this case will work. We'll get 17 over 10, which means our limit is a real number, so there is no vertical asymptote at x equals 6. So again, 2 points where a function is undefined, but only one of those is a vertical asymptote. And then in our last example, we'll proceed the same way. Factor the denominator to get x plus 7 times x plus 2, or I'm sorry, x minus 2. Setting that equal to 0 tells us that x equals 2 or negative 7 are our 2 points where the function's undefined that we need to consider. So if we take the limit as x approaches negative 7, if we factor the numerator, this would factor as 5x minus 2 times x plus 2 over x plus 7 times x minus 2. So in this case, factoring the numerator and denominator doesn't give us anything that will cancel. So if we try to plug negative 7 into the denominator, we would get 0 in the denominator. So this limit does not exist, which means that there is a vertical asymptote at x equals negative 7. If we try to take the limit as x approaches 2 of 5x minus 2 times x plus 2 over x plus 7 times x minus 2. Again, direct substitution will give us that 0 in the denominator, meaning that the limit does not exist. So again, we have a vertical asymptote at x equals 2. So in this case, 2 points where the function's undefined and 2 vertical asymptotes. But we always need to make sure that once we find any of those possible values where our function's undefined, that we're taking the limit as x approaches both of those to determine is that a vertical asymptote or is it just a hole in the graph.